In this presentation, we will discuss the basic philosophy behind the evacuations egress model, and we will look at how the model can be set up and some of the output that can be generated. The basic philosophy behind the model is that the human behaviour part of egress is much more important than the movement part. Here we're particularly interested in pre-evacuation or pre-movement distributions, the route decision making of occupants, and occupant load distributions, where we're interested in the number of people in the building and where those people are then distributed. So long as we can get a reasonable model for movement, then the exact details are not generally too important. The second part of the philosophy is the uncertainty in egress scenarios means that a probabilistic approach needs to be considered. The evacuations model uses a node-based network model. Rooms are specified as nodes, and these are connected together by paths. If we imagine a simple two-room model that leads to the outside, we would represent that as two nodes with a connection in between, and then a connection to this what we call a safe node. The strengths of the node network type approach is it's relatively easy to create the map, and we generally get rapid simulation times. However, there are weaknesses. We cannot resolve the location of individual agents, and the space representation is an abstraction of reality. Paths are used to represent corridors or stairs. We need to specify a travel distance and then include constrictions such as doors, and we typically will need to know their width. The evacuations model allows users to specify a range of different distributions for a number of inputs. Distributions include the normal, uniform, and log normal distribution. Occupants are represented by agents with specific characteristics. These characteristics will be their route choice, their maximum uncongested walking speed, and their pre-evacuation delay. Agent decision making is based on events being applied to those agents that then results in one or more potential actions. Agent movement is modelled by the standard SFP equations. Occupant density and path types affects walking speed, and constrictions are modelled using specific flows. There are a number of different route finding algorithms available in the model. The shortest travel distance to a safe node allows the agent to identify all of the safe nodes available and to work out which one has the shortest total travel distance. The least number of nodes algorithm allows the agent to figure out the minimum number of nodes that they need to travel through to reach a safe node. The shortest distance to next node algorithm, in this case the agent assesses the shortest distance to the neighbouring node to the one they're currently in. The longest travel distance, in this case the agent identifies all of the potential safe nodes and follows the route that provides the longest travel distance. In the specified safe node algorithm, the user can specify which safe node the agents need to move to, and then they will identify the shortest path to that particular specified node. The shortest travel to a randomly specified node starts to use the probabilistic capability of the model. In this case, the model randomly selects one of the potential safe nodes, and agents then follow the shortest distance to that random safe node. With the designated exit path algorithm, the user can set up specific paths that agents must follow. Typically, this might be paths that have exit signs on the route. The specified preferred path algorithm allows the user to set up pathways that might be preferred by the agents in the model. Typically, this might be having agents follow a route that represents the way they came in the building and the way that they then leave the building. The random path to next node is included for completeness, although not particularly useful. In this case, the agent simply selects a random neighbouring node. the path to the narrowest exit constriction allows the user to start examining the sensitivity of the scenario. And in this case, the agent identifies all of the potential safe nodes and then follows the shortest path to the safe node with the narrowest exit constriction width. The next node with least agents allows an agent to assess the potential delays depending on the size of queues that are using particular routes. The agent will choose the path that has the least number of agents using their the current routes available to them. Route choices can be combined by the user to create scripts. So for example, we might have an exit choice that specifies that agent select a fire exit route. If no fire exit route exists, then select the nearest safe node, but if there are several safe nodes then that are at equal distance, then select the least populated path. And the user can create multiple route choice combinations and apply those to multiple agents. Agents can be probabilistically assigned a number of characteristics, in particular their pre-evacuation delay time, their uncongested movement speed, and their exit choice behaviour. So for example, we might want to create a number of different agent types. In a hospital example, we might want to create staff who are aware of the building layout and know which is the quickest route to the nearest safe exit, whereas visitors might prefer to use the same path that they entered the building. In terms of populating the spaces, we can apply a fixed number of agents per node. We can apply a random number of agents per node. We can apply a fixed number of agents and then distribute those over 2 or more nodes of interest. Similarly, we can have a random number of agents distributed over 2 or more nodes. Or we might use a fixed or random occupant density per node. And when populating nodes, agent types can be proportionally selected. So for our hospital example, we might want 60% of the occupants are patients, 30% are visitors, and 10% of staff. The software allows for a fixed or random delay before an agent can exit a node. This has been useful for modelling refuge floors. We can apply this algorithm to specific agent types, and we can allow all agents to leave at a set specified time. This might represent the emergency services requiring a refuge floor be cleared at a certain point in the scenario. It's also envisaged in the future this algorithm will be useful for modelling lift, elevator and elevators, although this function hasn't been specifically tested in the current version. The input to the model is basically through XML code. This is a low-level way of inputting of creating the model, but it allows the user full power over all of the input. However, for geometry, we can use a freely available tool called Wired to create the nodes and pathways. So here I've got a version of the station nightclub building, and I've overlaid my node network representation of the building on a plan of the building, and we can see my nodes, connections and safe nodes. In terms of output, the model produces CSV files that can be pulled into spreadsheets, HTML documents that can be used to import into reports, and we can use the Wired software to provide graphical information. So here we've got an example again using the station nightclub scenario. On the left hand side, after 90 seconds, we are representing where the various agents are at that time, where the colour of the dot indicates the room that the agent started in. And on the right hand side, we're using the ability to use the grayscale fill of the boxes to represent occupant density, where the darker the grayscale, the higher the occupant density. We can also use Wired to create an animation of a simulation, and in this case here we're just animating the agents as they move from their starting nodes into their intermediate nodes and then their exit nodes, and once they reach their exit node then they're removed from the animation. Obviously, the dots here are representing the node that agents are in, but the position of the dot is not an indication of exactly where they are in that node. And we can rerun this animation as a cycle, but we will move on from here. On the final slide, we look at another way which we can generate output. In this case, we're looking at comparing the evacuation simulation with some high-rise building trial evacuations. On the left-hand side, again, we're using the ability to colour in the nodes to represent the stairs and landings to look at occupant density. Or on the right-hand side, we're comparing the output from a number of iterations of the evacuation model, represented by the grey scale, the grey area, which shows the range of results, and this is compared to the observation results shown as the dots. And so that ends this little presentation.